Hello and welcome to our webcast on social network analysis. We are 5 students from the University of Innsbruck analyzing the dataset provided by Yelp in its Dataset Challenge. We want to start with the webcast by giving you a short introduction on what SNA is before we go into details of the dataset and what we did with it. SNA is a set of methods for the analysis of social structures, or in other words, it is a way to study social relations among a set of actors. It is mainly used to find patterns in the interaction between people. The nodes in the network represent the people and groups, while the links show the relationship between the nodes. Let's come to the dataset. The Yelp Dataset Challenge is a program where the review platform Yelp provided parts of their data on businesses, reviews, and users for everyone who's interested in analyzing them. The Data Challenge is now in round number 8 and provides a dataset of 2.7 million reviews. The social network has 690,000 users and a total of 4.2 million social edges. As the numbers already show, the dataset is quite complex and forced us to focus only on parts of it. Therefore, we picked 5 cities and mainly focused on them. We chose Edinburgh in Scotland, Las Vegas, Scottsdale, Charlotte, and Phoenix in the US. Okay, let's get started with the actual work on the dataset. We made a short tutorial for you explaining how we imported and transformed the data to make them usable, how we reduced them to an appropriate size, which our computers could handle, and how we made analysis on the data.
Hello and welcome to the first video of our Yelp dataset analysis. In this video I will show you how we imported and transformed the Yelp dataset. The data are available in JSON format, and to make it usable for R we have to import it with the package JSON Lite. Other packages we use for transforming the data is the dplyr for data manipulation, the Margaret R package for getting a special operator, which is this one, and the deep tidier package for actually rearranging the data. If you're using these packages the first time, just install them with the install package function. It is important to mention that a package just needs to be installed once, but the loading has to be done for every new session. We want to load the dataset into the R environment, therefore we have to set a working directory to determine the location of our dataset. Go on session, set working directory, and then you can simply choose the directory where your data lays. Then we use the streaming function for importing the Yelp dataset. The streaming function is a function of the JSON Lite package. Because of the hierarchical data structure with many subcategories, it is necessary to extract the subcategories with the flatten function. Now we select the columns we are interested in. We are mainly interested in the user ID and in the friend ID, so we have to insert a minus in front of the column names we don't want, or we directly select the user ID and the friend. As we want to analyze social networks, users without Yelp friends are not of our interest. So we create a subset that excludes them. The resulting dataset will see as a user and next to him all his friends listed up. We need this data to be in a table that shows a unique and atomic friendship between two people. To transform the data into a table, we can use the honest function. The result is this user table 3. We can take a quick look at this user table 3. Have to wait. Okay, here we see the user ID and the respective friends ID. So you can see we have 4.2 million entries in this data frame. We do the same importing for the business dataset and for the review dataset. In the business dataset, we are interested in the business ID and the cities. In the review dataset, we want to analyze the business ID and the user ID of every review. Hello and welcome to the second video of our Yelp dataset analysis. We're using the same packages as in the first video. Just load them into your session and you're able to follow my instructions. We are starting with the reduction of the business ID dataset. Just have a quick view on this dataset. We are interested in the business ID of the businesses and in the city. We are reducing this dataset to all businesses that are located in Las Vegas. Therefore, we apply the subset function. We select all cities that are equal to Las Vegas, and we just want, as a result, the business IDs. Next, we are merging the Las Vegas business IDs with the user table 1. The user table 1, as we will see, is a data frame that contains the IDs of all users that provided a review to a business. Doing this, we have all users that made a review to a business that is located in Las Vegas. Because of the size of this resulting data frame, we are further reducing it to the top 10 reviewers, so to the users that made the most reviews to Las Vegas businesses. We can take a quick look at this data frame. Here we have the top 10 reviewers and the number of reviews they provided to businesses in Las Vegas. We merge this data frame with the user table 3. The user table 3 is a data frame that contains all friendship ties of the whole Yelp dataset. By doing this, we get a list of all direct friends or the direct neighbors of the Las Vegas top reviewers. For doing some calculation of basic network statistics, we'll load the iRef package into our session. Because iRef requires a special object to work with, we have to transform this data frame into an iRef object. Then we simplify it for deleting redundant edges. Now we are already able for applying functions that provide calculations and algorithms for network statistics. You can find the documentation of each of these functions on the iRef homepage. We run these functions all together. Next, we will load these functions into a data frame for making it readable. And we will take a quick look at it. Here we have the degree. The degree are simply a measure that counts the direct neighbors or the direct friends of a user. As we can see here, there's one user that has over 2,000 friends. What's also very interesting is the eigenvector centrality. You can see the users with the highest degree have also the highest eigenvector centrality. Eigenvector centrality determines the location in the dataset or in the social network. Last but not least, we want to know the correlation between this network statistics. We apply the core function and can have a quick look at this resulting matrix. Here we have the correlation between the network statistics. So we can see there's a very high correlation between betweenness centrality and degree centrality, also between eigenvector centrality and degree centrality. This means actually that users that are bridges between cliques are also the one with the highest amount of friends, and that the users that are the most central in the social network are also the ones with a very high amount of friends. This correlation between eigenvector centrality and closeness is lower, and between eigenvector centrality and betweenness is also quite high. It also means that the most central users are very likely to be bridges between communities or cliques within a social network. In this video, I will talk about largest cliques and communities. What is a largest clique? A largest clique is a special type of community where each member is a friend of each other member. The iGraph library offers a largest clique function. The input of this largest clique function has to be an undirected graph object. If your graph object isn't undirected, just type in this statement. We execute the code and we get a list of 18 elements, and each element contains 7 users. So we have 18 largest cliques of the size 7. Now we are talking about communities. If you have a very big data set, I recommend to use the cluster Louvain function. It does multi-level community detection in a very fast way. Also, this function requires an undirected graph as input. I transformed the graph Las Vegas object another time to another undirected graph. We execute this function, and as you can see, the communities were already calculated. Next we can look what's the modularity of this cluster Las Vegas. It's 0.52. Next, maybe it's also interesting knowing the membership, so which user is in which clique. This, here we can see the output list, and last, what's very interesting, maybe most interesting thing, the size of the communities. Here you can see as a very good summary there are 9 communities, and for example community 1 has 540 members while community 9 has 86 members.
Thank you for watching the tutorial. I hope you liked it. Okay, let's do some theory. Since you now know how to handle the data, we will give you some basic theoretical information on 5 analyses we conducted. For each of these analyses, we provide you with a small exemplary picture of a network which shall illustrate the results for the analysis. We also provide you with some practical examples of our own data. But first, we want to show you a short tutorial on how to create graphs in a program called Gephi.
Now I give you a quick overview of Gephi. To use Gephi, you first have to import your data. Therefore, you go to Data Laboratory, Import Spreadsheet. Here you have to import the needed data as a CSV file. The needed columns are ID, source, and target. The source is equal to the user, the target is the friend of the user. Then you click Next and Finish. So now you can see the imported data. In the next step, you go to the sheet overview. The overview provides you a first impression of the analyzed data. As you can see, it's still a bit messy. To get an appropriate layer, you need to apply algorithms. We first use the Force-Alt+2 algorithm. The algorithm simulates a physical system. Nodes repulse each other like charged particles, while edges attract the nodes like springs. Now you can see a structure, but the nodes are not easy to identify by now. To change this, we use another algorithm, the Ivan-Hu, which works similar but expands the network for a better overview. After several runs of this algorithm, you can see that the data is getting more informative. In the next step, we will make some statistics. Therefore, we calculate the average degree by clicking on the Run button. As a result, received the degree distribution. Furthermore, we need to calculate the network diameter. So to highlight the degree, we go to partition, degree. As you can see here, every degree has a different color. There are several palettes where we can choose, and we push the apply button, and now we can see the colored coding of the nodes. Here the first degree is colored pink, the second blue, and so on. If you see another centrality, you just need to click on the size button. Then, for example, you choose the betweenness centrality. Clicking on apply, and the result now you can see the different sizes of the nodes showing the size of the betweenness centrality. If you like to export this analysis, you have to click on preview, refresh the settings, and now you see the adjusted picture. Then click on File, Export, and you can export the visualization in the SVG, PDF or PNG format.
Now that we know how to create graphs, we can continue with the analysis and interpretation of them. Communities consist of nodes that can be grouped into sets where each set of nodes is densely connected internally. We first did community detection with the multi-level modularity optimization algorithm for the network Las Vegas to find out who the communities are. The tables show the number of communities and the size of each community. As you can see, we found out that there are 9 communities built around the top 10 users, meaning that 2 users belong to the same community. This community is the light rose one, which is a little bit spread over the network. Next, we analyzed the degree centrality, meaning which nodes, or in our case users, are most central with respect to spreading information and influencing others in the immediate neighborhood. It is the number of direct connections a node has. The most active nodes in this example are node 3 and 5, with 4 connections each. Let's have a look at our data. Our top 10 users are marked with arrows and represent the so-called connectors or hubs in the network. Common wisdom in personal networks says the more connections, the better. But this is not always the case. What really matters is where those connections lead to and how they connect the otherwise unconnected nodes. How can we find out who the unconnected nodes are? The key word is betweenness centrality. The betweenness centrality is a measure about the shortest path between 2 people in the network. If a node has a high betweenness centrality, it is more likely to have more control over the network, because more information will pass through the node. One of the other sides of the coin, exactly this node or user, can also be a single point of failure. Here, node 5 has a great influence over what flows in the network and again what does not flow. In our network, Las Vegas, we can see 9 bigger nodes that represent the so-called gatekeepers. One of the top 10 users is consequently not a gatekeeper, but rather part of one community for which another one plays the role of a gatekeeper. The next analysis is closeness centrality. It provides information about how fast a person could reach everyone else within the network. Therefore, it determines the shortest path from one node to every other node. In the example, user 3 and 5 have high closeness centrality and an excellent position to monitor the information flow in the network. In our network, the top 10 users have the highest closeness centrality, which is not really surprising as we selected these users as a basis for a network. Eigenvector centrality is an extension to degree centrality. but not all users within a network are equally important, hence this measure takes the relevance of each connected node into account. A node receiving many links does not necessarily have a high eigenvector centrality, because it might be that all linkers have low or null eigenvector centrality. Moreover, a node with high eigenvector centrality is not necessarily highly linked, because the nodes might have few but important linkers. In the example, node 3, but also node 2 and 5 have a high eigenvector centrality. We had a deeper look on the users itself and discovered that not only the top 10 users have a high eigenvector centrality, but also several other users. Many users have a good position in terms of important relationships. Here the coloration is, the darker the green, the higher the eigenvector centrality. The last analysis we conducted is regarding cliques. Cliques are subgroups in which all nodes are directly connected to each other. The idea of a clique is relatively simple. It is a subset of a network in which the actors are more closely and intensely tied to one another than they are to other members of the network. Formally, a clique is a maximum number of actors who have all possible ties present among themselves. In our case, we wanted to find out who the largest cliques in the network are and how large they are. We found that 18 largest cliques exist in Las Vegas, from which each has 7 clique members. A person that is a member of one of these cliques can reach every other member of the network by going through 2.8 nodes. We also analyzed this for the whole network and discovered that each user can reach one of the cliques with a mean distance of 7.26 connections. This is equivalent to the magic number of 7 connectors, also known as the smallest world phenomenon by Milgram, over which you also might know, for example, the President of the United States. When digging deeper into the analysis, we figured out that around 800 from 4,800 users have a direct connections to more than 2 of the top 10 reviewers. So the reach of these top 10 users is quite high. We also found that there are 30 users that are more central than the 9th of the top 10 users, which is quite surprising. That means that there's one user that writes a huge amount of reviews but is not as central as the other ones and his reviews might not have such a great impact. Now we can formulate some hypotheses. He might be a real reviewer and does not care about connections in the network, but he also might be paid to review as many businesses as possible. These were our main 5 analyses we wanted to share with you guys. Now we'd like to tell you something about the challenges we came across and the limitations in our analysis. Probably the biggest limitation has been working memory of our computers. The processing time for some of the calculation was simply beyond their capabilities. There was, for example, one calculation running for more than 3 days without any result. Moreover, we had graphics of the network stored as PDFs, which then simply were too big to be opened. As I said in the beginning, due to the volume of the data, we had to split and reduce them in order to receive results. The initial dataset was set up of a number of different communities. Extracting these communities with different algorithms was not possible because of the sizes of the dataset. Therefore, we had to create artificial subsets with the limitation that network statistics are less meaningful in the context of the whole dataset. Thank you for watching, and we hope you enjoyed our webcast on social network analysis.